Okay. Hi, everybody. So this is going to be the first of these kind of concept videos where I just kind of explain one particular concept for the class so you have it to refer to. The specific concept I'm going to be talking about today is induction, and particularly how induction works in circuits. Just before the end of break, we talked a little bit about this concept of induction and inductance. This is basically a phenomena whereby if you change a current in a coil of wire or a wire loop, that will induce a current in another wire. The reason this happens is if you change the current in this loop, you will produce a magnetic field that changes, and you know a changing magnetic field can drive a current. The inductance is a measure of how well that happens. What's important to understand is that this process can occur within a single loop. This, for example, is a wire loop that's generating a magnetic field. If you change the current in that loop, you will change that magnetic field and try to induce a current within the loop itself. In effect, if you try and change the current, you produce what's called a back EMF. You produce an electromotive force that tries to drive the charges around this loop. And how well it does that is quantified in terms of a quantity called the self-inductance, or usually just the inductance, and is designated with this letter L. So there's this relationship between the EMF, the electromotive force in a circuit, and changes in the current over time. So delta I is the change in current per delta time, the change over time. So if you have a bigger change over time, so a faster change, you'll get a bigger EMF. If you have a smaller change over time, a slower change, you'll have a weaker EMF. And what relates those two quantities to each other is this thing called the inductance L. Note L has units of volt seconds per ampere. This is not ohms, that's volts per amp. It's something different. It is called, because everything has to have a name, a Henry. And different circuits, different current loops have different inductances or Henrys. An important thing to note about this expression is this minus sign. Basically, anytime the current changes, there's an electromotive force which resists that change. Basically, the electromotive force will push the electrons in whatever direction they have to go to keep the magnetic field constant, which is equivalent to keeping the current constant. So this is something that naturally fights changes in currents. And how well a circuit fights those changes is quantified in terms of this inductance L. This is just like the resistance of a circuit. It is something that relates properties of the current to properties of the EMF. And so how that relationship, that quantity depends on what your circuit looks like. And just like we had for resistors, there is that quantity, the inductance, doesn't care at all about what the voltage or the current is, at least in simple cases. It cares about the shape of the circuit. It cares about basically how those wires are distributed in space. Now, this is just like with resistors, where we had an expression that told us the resistance of a circuit element, which depended on its length, its area, and its resistivity. You can calculate this inductance based on quantities like, say, the number of loops, or the area of those loops, or the length of the system. I'm not going to go too far into this. You have one problem which asks you to use a formula like this. So specifically, if we have a solenoid, that is just a simple bunch of loops of wire all hooked up in series next to each other so that the currents are all coming out on one side and in on the other, this thing has a well-defined inductance, which is given by mu naught, that's that 4 pi times 10 to the minus 7 number we talked about, n, the number of loops, a, the area of each one of those loops, divided by the length of the entire solenoid. This is just quantities you know, and you do have one problem where it's basically asked you to calculate this given all of these parameters. So this is another property an element in a circuit can have. And so it is, as I said, very much like resistance. Remember, resistance is something that relates currents to electromotive forces. If you have a certain voltage or EMF across your circuit, and you have a given resistance, you can figure out the current, or vice versa. This relation now doesn't connect the electromotive force or the voltage to the current, it relates it to changes in the current. But it's still a similar form. And this L is what relates the changes in the current to the EMF, just like how resistance relates the current to the EMF. That's what it is. But you can also calculate it based on properties of the materials themselves. Remember, resistance is resistivity times length divided by area. For solenoids, the inductance is proportional to the square of the number of loops times the area divided by the length. Now, this is another thing that exists in circuits, but it has a different behavior than resistances, in that this is only relevant if the current changes. And so we're going to look at a few examples where that can be relevant. For example, let's consider the following circuit. It's got a battery in it, it's got a resistor in it, and it's got an inductor. For historical reasons, inductors are always shown as a bunch of little loops, just like resistors are always shown as little squiggly lines. So this is a thing with an inductance L. What is that L? We don't know yet. Now, in this case, we just have a simple sitting thing. The voltage is a constant across the circuit, the EMF is a constant, and the current is a constant. There's just a current flowing around. Well, in this case, what's the current going through the circuit? Well, I'm going to ask you to think about that. Does this inductor play any role in this case when the current doesn't change? The answer is no. If the current doesn't change, there's no change in current. So the inductor does absolutely nothing. The current flowing through this loop is just given by Ohm's law. The only thing that matters is this resistor. So we can use V equals IR, or I equals V over R. If this is a 10-volt battery hooked up to a 10-ohm resistor, it's just 10 over 10, 1 amp. So in these cases, which is everything we've talked about thus far, the inductor doesn't matter. The inductor does matter, though, if we ever change the current. And a simple example of that is this circuit, where we now have a switch, where we can basically take the battery out of the circuit by moving the switch from position 1 to position 2. If we move the switch at that time, the circuit goes from having a voltage across it to having no voltage across it. So what happens here? Now this inductor plays a role. But to see what that role is, it's useful to first consider the case where there is no inductor. If there is no inductor and you just have a resistor, you have current happily flowing through the loop, then you throw the switch, there's no current flowing through the loop anymore. So the current goes from some level, and then it drops to nothing and becomes nothing. That's what would happen if there was no inductor in this circuit. But if you have an inductor in this circuit, something different happens. What happens is this. As you throw the switch, the current starts to try and change. But that change produces an electromotive force in the inductor. The inductor doesn't want the current to change. So it produces an EMF that allows the current to keep going for a while. So instead of dropping off immediately to zero, it takes some time to do that. This is what inductors do. And remember, any wire loop has inductance. This, not instantaneous change will always happen. Because if nothing else, this circuit is a loop. It has some small inductance. Now, the thing about this is actually a functional, the way this changes with time is actually very predictable. And it follows what's called an exponential behavior. So in the case where we throw the switch and turn it off, the current falls in a very clear and well-defined way, given with a very particular time scale, which is here designated with the symbol tau. Tau is a time which is given by the ratio of L over R. So it's the ratio of the inductance to the resistance. That has units of time because inductance is ohms seconds. Divide by ohms gives you the right thing. Every one of those time periods, which could be 10 seconds, could be 1 millisecond, whatever it is, the current in this case will fall by a factor of what's called 0.368. This is a very specific number. It's related to this constant known as E. So in one time unit of L over R, the signal drops from I naught, whatever the current was to start with, by a factor of 0.37. After another time, so we're now at time 2 tau, it's dropped by another factor of 0.37. So the current has dropped by 0.37 times 0.37, or 0.14. After another time, it's 0.37 times 0.37 times 0.37, which is about 0.05. Every extra time, you have to multiply an extra 0.37. This is the nature of exponential decay. It's also the nature of exponential growth. So the current will fall at first quickly and then more and more slowly until it hits zero. This is what happens if you pull the battery out of the thing by throwing the switch. What if you put it in? Or, sorry, before we get into that, now this is just a few specific cases, but you can write this in terms of a particular formula. This is the formula for what the current is as a function of time. Its I is whatever the current was to start, times E, which is the exponential constant. Just to say, this thing is a number. It is a number that happens to be 2.73. You can look that up if you want. It's a special number. Why it's special, that's a question for another world. It is that number raised to a power. It's raised to the ratio of the time t to this ratio L over R, which is a time constant. So it's t over tau, which is a unitless quantity. So this is the exponent, is the form, and you can plug in any time you want to get how the current falls. This behavior occurs also if you go the other way. If you throw the switch so that now we go back to having the battery on, what do we see? Well, at first the current rises quickly, but as the current rises, at first the current rises quickly, but then it slowly stabilizes at the particular current set by the resistor, set by Ohm's law. Again, the rise starts off fast and gets slower and slower and slower. It's described by this formula, where the current is given by the ultimate value of the current times 1 minus this number e raised to the power of the ratio between the time t and the ratio L over R. So what L is doing is it's not setting what the absolute current is, it tells you how quickly the current can change. And you've got one particular problem that asks you to use these formulas, which I'll show you in the next video how to approach that one. Just because it is worth understanding what these formulas, how these formulas work. Although I will say, because these formulas can be a little twitchy, I'm not expecting you to do any of these particular explicit calculations on the exam. But please look at the next video to see how we do these types of problems. Okay, thank you. And thank you for your time.